Okay, in this video we're going to prove some more facts about cyclic groups. So let's just recall what a cyclic group is. We say a group G is a cyclic group if there is an element in G where G is equal to the cyclic subgroup generated by G. In other words, every element of capital G can be written as a power of little g as that exponent runs over all integers. And we generally say here that G is generated by little g. Okay, so you might think, well, what about the subgroups of cyclic groups? And it turns out that every subgroup of a cyclic group is cyclic. And so let's go ahead and prove that. So let's suppose that we have a cyclic group G, and so we'll say G is the cyclic group, and we have H is a subgroup of this cyclic group. Okay, so to get ourselves started, we'll consider the following subset of the natural numbers. So we'll let S equal to be all natural numbers A, such that G to the A is an element of H. Okay, so now notice that this set, well, it's obviously a subset of the natural numbers, so it has a minimal element. And let's call that element M, which is in S, which tells us that G to the M is in H. Great. So now the next thing that we want to do is take another element from H. So take another element from H. Notice we can write that as G to the N, which is in H, because every element from H is of the form G to some power, given that H is a subgroup of this cyclic group. Great. And now we don't have a lot of tools yet, but one tool that we do have is the division algorithm. So let's perform the division algorithm with M and N. Great. And notice that's going to give us the following. So we can write N equals M times Q plus R. So again, that's the division algorithm. We have divided N by M. We've gotten our quotient and our remainder, and we are guaranteed to know that our remainder is between 0 and M minus 1. Okay, good. Now, what we want to do from here is take this Gn and then rewrite it using this division algorithm. So notice that is G to the MQ plus R. Great. But that's exactly equal to G to the M all to the Q power times G to the R power. Good, just by some exponent rules. But now, notice we can solve this equation for G to the R. That tells us that G to the R is equal to G to the N times G to the M to the minus Q. Great. But now let's recall that G to the N was in the subgroup and G to the M was also in the subgroup, but that makes this combination in the subgroup. So in other words, we have this is in the subgroup H. But let's look at this. We have G to this power R is in H, but R is between 0 and M minus 1. But we know that this element M from S is the smallest such that G to the M is in H. So that means R is not allowed to be anything except for 0. Because notice if R is equal to 1, well, that's going to contradict the minimality of M. If R is equal to anything up to M minus 1, that's going to contradict the minimality of M, because that means that G to some power smaller than M would be in H. So the only thing left is that R equals 0. Great. But now notice if R equals 0, well, let's go ahead and clean up the board a little bit and see what we get knowing that R equals 0. Okay, so on the last board, we proved that the remainder after doing some division algorithm was equal to 0, which told us that when we took any arbitrary element from H, which we called G to the N power, we could write it as G to the, let's just remind ourselves, this is to the MQ times G to the R, but R was equal to 0, which makes this term just the identity. So this is equal to G to the M to the Q power, but notice that is an element of G to the M. Great. So now what that tells us is that this subgroup H is contained in this cyclic subgroup generated by G to the M. Great. So now the next thing we need to show is that this cyclic subgroup generated by G to the M is in H, but that's actually quite easy, and that is because G to the M is in H. That tells us that this cyclic subgroup G to the M is actually just a cyclic subgroup of H itself, viewing like H as a group. So that gives us this double containment of these subgroups, from which it follows that H is exactly equal to this cyclic subgroup. And that finishes our proof. Okay, good. That's a good place to end this video.